Hello, honors topics in physics students. A little bit more on waves today. So first off, if you were to shake a slinky, and this would be better had we all had the experience of shaking slinkies and observing what happened. But if you were to shake a slinky and it was connected to a rigid boundary, you know, like somebody's hand or a chair or something like that, and you were to shake it, you would see waves that look something like this. You would just see waves flow down from you down to the other side. But this is not what you actually see. What you actually see is the waves that you're sending down and those waves that are reflecting back, and you see them at the same time on the rope. So if you happen to shake at just the right frequency, or in order to make a wave such that that wave is twice the length as the distance, so you have half a wave between you and the boundary, and then you were to, what would that wave look like when it reflected back? Remember, waves off of rigid boundaries are inverted, so when it reflected back, it would be flipped over to the other side. Now, meanwhile, you're going to send the other half of that wave, because you sent an up hump, okay, and then you're going to send the other half of that, which is a down. Okay, now meanwhile, that up that you sent reflected back and is going to be at this on the rope at the same time. So you're going to actually have two down humps on that at the same time, and the result is going to be a bigger down hump. What kind of interference is that? That is constructive interference, because they added together. Okay. Now, if I shake with twice the frequency, what's going to happen to my wavelength? Well, is my wave going to get longer or shorter if I increase the frequency? Well, if I increase the frequency, the wave is going to get shorter, and if I double the frequency, the wavelength is going to halve. Okay. So now, instead of being able to only fit half a wave between me and myself and the boundary, I can fit the whole wave. Okay. Now I'm going to send this wave down. What is this wave going to look like when it's reflected? Remember, it's going to be inverted, but as we talked before, okay, it's not going to look like it's inverted. It's going to look like the same wave traveling in the opposite direction. So it is inverted. Okay, so what's this going to look like on the rope when I keep sending these waves? I'm going to get constructive interference again. Okay, and I'm going to get a big up and a big down. Okay, so this is kind of like resonance, which we briefly talked about with the swings. If you vibrate something at the right frequency, you get a larger amplitude oscillation, and that's what we're seeing here is large amplitude oscillations with lots of constructive interference. Okay, so these waves that you see that we've been talking about are called standing waves, and you really don't know what a standing wave is yet because we haven't really seen one in motion. And it looks like they're basically just standing still. It doesn't look like that very first slide where the waves were traveling from me down to the other side. It looks like the ups and downs are just oscillating up and down. But I want you to notice some topography of these waves. There's going to be points that aren't moving at all. Okay, thus part of the standing wave. These are called nodes, and this is the same node that we talked about when the wave crosses the baseline. The parts that are oscillating the most, so this up is the maximum, is called an antinode, and this up will in a very brief time become a down. Okay, and you'll see what I mean. Those ups and downs are called antinodes, and they're the result of constructive and destructive interference, and of the waves that you're sending down, the incident waves and the reflected waves. So this is kind of in slow motion, which is nice because it gives you some time to comprehend what's going on. So I'm going to hit start, and I'm over here, and I'm sending waves down. So the red lines represent the incident waves, or the waves that I'm sending down. The black dots represent what you actually see on the rope. Okay, now in a minute, these red waves are going to hit this boundary and they're going to flip. They're going to become reflected waves, and they're going to become blue. Okay, so you're going to see red, you're going to see blue, and you're going to see the black dots. So here comes the blue reflected waves. Okay, and then what you actually see on the rope is represented by these dots. Okay, and the dots that you see on the rope represent the standing waves. Okay, so notice, first off that the antinodes really just flip from being a crest to a trough. They just go up and down. But the nodes are perfectly still. And I don't know why it's stopping and starting here. So again, it kind of looks like it's just standing there. So that's why it's called a standing wave. And again, this is the result of constructive interference, then destructive interference, and then constructive interference. Okay, right now because the crests overlapped. Okay, and then when they're opposite, then that's destructive interference. And you've got to shake it at just at one of the right frequencies in order for this to happen. So anyway, that's kind of nifty. If you have a slinky, get with another person and shake it and try to set up one of these standing waves at home. They're kind of fun to play around with. So are slinkies just in general. So that is basically what a standing wave is. So there's different standing waves. So this is the first standing wave, and I have one antinode and two nodes. And this is the lowest frequency standing wave. Okay. Now if I shake it twice as fast, okay, I'll pick up the second standing wave, okay, and I'll have two humps, okay, between my boundaries. So I'll have two antinodes and three nodes. One, two, three nodes. And then the third standing wave, I'll have 1, 2, 3, 4 nodes and 3 antinodes. So basically the standing wave harmonic, as it's called, is just the number of antinodes. The fourth harmonic is 1, 2, 3, and 4 antinodes. And these are achieved just by shaking at increasing and increasing frequencies. What happens to the wavelength as I increase in harmonic? Okay. Well, the first one, I could only fit half a wave between it, so the full wavelength is out here. The second harmonic fits snugly right in between, okay, and so it's shortened. And then the next wavelength is from here to here, so it's shortened. And the next wavelength is from here to here, so it's shortened even further. So as you go up in harmonic, the frequency increases, but the wavelength decreases. And you should be familiar with that concept. As frequency increases, wavelength decreases. Okay. But one thing to keep a note is that all these cases, you start and end with a node. Okay, so that's where it's touching the poles and that kind of thing. Okay. All right. All right. So these are examples of, this is the first harmonic, okay, with one antinode. Okay, this is the second harmonic with two antinodes. And this is the third harmonic with 3 antinodes. And this is the fourth harmonic with 4 antinodes. And notice that the greatest frequency is this guy over here, and the slowest frequency is the first one. Okay? Let you process that for a second. Okay. A rope is stretched between two poles 1.6 meters apart. What are the wavelengths of the first two harmonics, or the first two standing waves? And if the waves travel down the rope at 4 meters per second, what frequency will create the first standing wave, or the first two standing waves? Okay, so the poles are 1.6 meters apart. So I've got these lines here as drawn as the poles is 1.6 meters apart. And we want to look at the first harmonic and the second harmonic. Well, the first harmonic has one antinode, okay, and so that's one hump. Okay. The second harmonic has two antinodes. And so now we got to figure out the wavelength. Well, one antinode, that means half of a wave fits between the poles, which means the total wave must be twice the distance between the poles, which is 3.2 meters. And if we look at the second harmonic, well, I've got two antinodes, and that's one full wave. and therefore the wavelength is just 1.6 meters, the distance between the poles. Okay. Now, if the waves traveled at 4 meters per second, what is the frequency that we're jiggling the string at? Well, we use our friend v equals lambda f, and so our v, our velocity, is 4. For the first harmonic, our wavelength is 3.2 meters, and then solving for f, we get the frequency equals 1.25 hertz. Okay. For the second, we use the same velocity, because the only thing that affects the speed of a wave is the medium, and we're using the same medium, so it's the same velocity. And so the wavelength here is 1.6 meters, and solving for the frequency, we get 2.5 hertz. Okay, so the second harmonic frequency is always going to be twice the first harmonic frequency, and the third is always going to be 3 times the first frequency, and that kind of thing. So it's a really easy relationship. Okay, so if you start and end with an antinode, start and end with a node, you're always going to get this, at least at times, this constructive interference, although at times it is destructive as they pass through each other, as they're moving through each other. If you vibrate in between one of those frequencies, they're always going to cancel. You're going to get a bunch of destructive interference. So only certain frequencies will create standing waves, because you need to achieve that constructive and that destructive and constructive interference. So go ahead and work on your homework, and we will talk to you later. Bye.